So we're in the triple snake business here, and we covered the theoretical aspects in the previous clip, and now we want to start doing some examples. And the first one is going to be a simple example over a simple domain. So I remind you that a simple domain is a domain where it's a domain in three-dimensional space. In one of the coordinates is bounded between two fixed constants. The second coordinate is bounded between two functions of the first coordinate, and then the third coordinate is bounded between two functions of the first and second coordinate. That's a simple domain in R3, and let's do an example. So let V be the pyramid I'm going to draw it right away. In the original problem, it was prescribed in terms of its vertices. Okay, so this is the point 0, 0, 0. This is the point. I want to make a bigger drawing. I don't like it already. Let me make this bigger. Let's move the word pyramid. Okay, much better. Okay, so we have 4 points here. This is the point 0, 0, 0. Over here on the x-axis, there's some point which I'm going to call A, 0, 0. So there's some parameter A here. Over here is going to be the point A, 0. So you can see the tails of the A's, which what makes them different than the zeros, right? I hope it's not too small. And then up here is going to be the point about up here, I think, like this, is going to be the point A. Okay, so this is A on the x-axis, this is A on the y-axis, so it's A0, and this is A on all three axes. Okay, and the pyramid is formed by these 4 vertices, so I have to connect them. So let's connect these two, and these two, and these two. So this is the base of the pyramid. It's in perspective. It's lying on the floor, on the xy plane. Do you see a 90-degree angle in this triangle? Where? Exactly. This is a 90-degree angle. Right? Does everybody see that? And then there are, bless you, and then there are all 3 vertices on the bottom have to connect to this top one here. Like this, and like this. Okay, so now let's dot this, because this one is in the back. And in fact, the y-axis here is in the back also. Clear? Is it clear what the pyramid is? Okay, so does everybody see it has 4 faces? 3 of them are going up. This one is facing us. This one is kind of in the rear, and this one is on the side. And there's the bottom, which I drew first. Clear? Is it clear what the domain V is? And now, remember, this is the domain over which there lives some function, which I'm going to tell you what it is in a minute, and the graph of the function I can't even draw. It's something in another 4th dimension. Okay? Okay. So, and we want to calculate, the triple integral over this domain V, the pyramid, of the function x, y, z, that's the function of three variables, dx, dy, dz. Okay, that's the example. So the first thing we have to decide is, are we indeed dealing with a simple domain? Can we write this domain such that one of the variables is between two fixed constants, then the other one is simple with respect to that one, and the third one between two functions? And the answer is yes. And we even have several choices here. So let's choose x to be, so let's rewrite v. V equals the set of all the points x, y, z, such that, and the restrictions are going to be as follows. X is going to be between 0 and a. Do you agree that those are two fixed constants, and any point x, y, z in this pyramid is between 0 and a, the x coordinate? So x is between 0 and a. Now what about y? For every fixed x between 0 and a, the y's range from here all the way to this dotted line, right? So what is this line? Well, 0 is correct, but it's not detailed enough in order to understand what we mean. Right, y equals 0. Do you agree that this is the line y equals 0 in terms of the xy plane? What is this line here, connecting 0, 0, 0 and a 0? Y equals x. So the y's are restricted between 0 and x, namely y equals 0 and y equals x. Clear? And now, for every fixed point xy in this bottom face on the floor, the z's range from the floor, what is the floor in terms of x and y? Z should be restricted between two functions of x and y. What is the floor as a function of x and y? It's z equals 0. Do you agree? Do you understand why I'm saying it this way? Okay, so z is between 0, that's the floor, that's the function f of, the graph of the function f of xy equals 0. Do you agree? And the top of the pyramid. Well, not the top, the face that's facing this way, maybe let's shade it, this face here. I don't know if this shading just made life simpler or more confusing, but this is the top. So for every point here, the z ranges from the floor till it hits this plane. Okay? And what is this plane? Do you agree that this is a plane? Okay? What is the equation of this plane? Well, you can either see it from the picture. Okay? What do I mean by see it from the picture? Well, you can imagine this plane continuing here, right? You can draw the point above here, which is going to be the point 0AA, which is going to sit above the y-axis here, and continue this. And then you can see that this is simply the plane y equals z. Okay? Or you can find the plane using 3 points. This point, and this point are 3 points on the plane. You know how to find the equation of the plane given 3 points, right? So anyway you do it, this is the plane. So this top plane is the plane y equals z. Does everybody agree? And the equation is therefore going to be z is restricted between 0 and y. And here we have to close this. So this is the domain V. V is this entire pyramid in here. Yes?
Can you show again how you see that?
Well, the question is, can I show how do I see it? But take a step back. Suppose you don't, you know how to find it. Right? You have 3 points. Finding a plane through going through 3 given points is something you know how to do, right? You can, for example, connect pairs with vectors and then find the the normal, using the vector product, and you know how to do it, right? Okay. Now I'm trying to say that I can actually see this without doing the formal calculations. I don't want to blur the picture, okay? But I can, maybe I'll blur it in a very fade. I can draw the point above here, above this point. So this is the point 0a0. Do you agree? This is 0a0. And above it, when I add a on the z-axis, this is going to be the point 0a. Do you agree? And this plane, this top thing, actually goes through, is lying up there. So this picture is in perspective, right? But if I think about it, it's simply the plane that crosses the yz plane precisely like that. That's the top of the pyramid. And it's the plane y equals z. For any x, it's the same. Do you see that? Good? So I can say that this is the plane y equals z without going through the formal calculations. But if you don't see that, and that's fine. Sometimes seeing things like this is more tricky or more confusing or may lead to more mistakes than just doing the straightforward routine calculation of finding a plane through 3 given points. Okay? Okay, so let me erase this because I think it might blur the picture. Okay, so do you agree that this is a simple domain? Okay? Now what is the integral? The triple integral of the function over this domain V is going to be, here it is, the triple integral over V of the function x, y, z, dx, dy, dz equals, and I'm going to just write it as iterated integrals, and it's of course important, the order. So the outer integral dx, where x ranges, let's write all the details. X ranges between x equals 0 and x equals a, and those are constants, therefore it can be the outer integral of, then we have the integral where y ranges between y equals 0 and y equals x, dy of, and then we have the integral where z ranges between z equals 0 and z equals y, dz, and here we have the function. Do you agree that this is the iterated integral corresponding to the triple integral that we want to solve? Good? Okay, and now it's all a matter of calculation. Once you got this far, you're back in Calc 1. Okay, it's just calculating single variable integrals. How do we work them? Where do we start? From the inside out. Why? Because when we calculate this one, there are x's, y's, and z's. It's an integral dz. The z is going to go away, but x's and y's are going to still be around. Okay? Then when we open the middle one, the y's are going to go away, and after we open the outer one, the x's are going to go away, and we're going to be left with a number. In this case, the number is going to have a's in it because a is a parameter. Okay? So let's do that. So I'm not touching the outer ones, x equals 0 to x equals a. It looks kind of, I don't know, babyish to write all these details. I really recommend doing it. Okay? It saves so much confusion and so much mistakes, like little typos and little substituting the wrong variables and things you do without thinking too much. And when you write it like this, it simply saves you a lot of trouble. Okay? So this is the integral dx of the integral from y equals 0 to y equals x dy. And now the inner integral, x, y, z, dz, is going to be x, y, z squared over 2 evaluated between z equals 0 and z equals y. Do you agree? 1 snake down, 2 to go. Now I have to plug in the top minus plug in the bottom, right? That's how we do single integrals. That's a Newton-Leibniz formula, antiderivative. So it's the integral from x equals 0 to x equals a dx of the integral from y equals 0 to y equals x dy of xy times y squared, so it's xy cubed over 2, and when I plug in 0, I get nothing. So this is it. Okay? You should verify at every step that it compiles in the sense that once you got this far, there should be no z's left. Okay? If you still have z's, they're never going to go away and something is wrong. Do you agree? Okay? Good. Let's continue. So it's the integral from x equals 0 to x equals a dx of, and now I need the derivative in terms of y. So what's the antiderivative of y to the power 3? Right. So it's going to be x y to the power 4 over 4 times 2 over 8. So it's x y to the power 4 over 8 evaluated between y equals 0 and y equals x. Do you agree? Good? Okay, what's that? So it's the integral from x equals 0 to x equals a. When I plug in x, I'm going to get x times x to the power 4, so I'm going to get x to the power 5 over 8. When I plug in 0, I get nothing, dx. Only one snake survives, only one variable should survive. You should see no more y's here. If there are still y's running around, something is wrong. Okay? Good. What's the antiderivative of x to the power 5? Right, so it's x to the power 6 over 6 times 8, which is 48, evaluated between x equals 0 and x equals a, and the final answer is a to the power 6 divided by 48. Questions? Good? So the calculations are in fact boring, and I'm usually not going to do them, at least not this slow, okay? Because it's all just calculating single variable integrals and just paying attention not to make careless errors, like writing the integrals in the incorrect order and solving the inner one for y and then being left with z's that you can never get rid of or things like that. Okay? So it's important to do them in the correct order, and solving them is just being careful about which variable you're doing at every step. Okay? Good, everybody? Okay. So when the domain is simple, and you might be thinking, wow, this was not simple. This was, wow. So the answer is yes. The three-dimensional shapes are not always simple to grasp. Okay, the word simple refers to a mathematical term referring to is the domain simple in the sense that blah, blah, blah. But seeing this and being able to transfer from this to the iterated integral simply takes some practice. Okay, like many things. You have to do a few and get used to seeing this, and it sometimes is a bit challenging at first. What we're going to do in the following examples, which are going to be in the next clips, we're going to tackle domains which are not simple, at least not simple enough at first, and we're first going to need to do a change of variables. Okay? And changes of variables in three variables are a bit more challenging, but still standard. Okay? Same ideas as in double integrals. So that's going to be in the next clip.